week. Yeah, so we continue to work according to the week plan, and today the idea is to finish the longest path application of the representative sets and to start towards proving the Balabash lemma for Metroids, and which will bring us to another set of new applications. But first of all, a reminder from the yesterday lectures. So yesterday I defined what is a representative set. So let me just repeat this definition. So the definition is if I have a family F of sets of size A sets, then the family F prime B represents set F if for every set B of size small b, such that if there exists a set from the family F which is disjoint with B, then there also should be a set A prime from family F prime which is disjoint with B as well. So that was the definition of the representative sets. And also I spent quite some time yesterday arguing that by Balabash lemma, we know that for every family of sets F, there is a set F prime, which is a subset of family F of size at most A plus B, choose B, that B represent the set F. So that will happen yesterday, and also yesterday I gave an algorithm which computes B representative set, and its outputs representative set not of size A plus B choose B, it's a bit larger set, so it's the set of size 2 power A plus B plus small o of A plus B times logarithm of n, and the running time of this algorithm is the size of the family power times 2 power A plus B and then log n. So this is what happened yesterday. And then I said that I want to apply this representative set algorithm. I want to apply it to the longest path problem. So what is the longest path problem? I have a graph G. You give me an integer k as the parameter, and then the question is if there exists a path of length at least k vertices. Right? So this is a famous generalization of the Hamiltonian path problem, or a Hamiltonian path problem with a special case of this problem for k equal to the number of when k is equal to the number of vertices of the graph. Once again, I'm using this algorithm for representative sets. And I want to use this algorithm to compute the longest path in time 4 power k, roughly, times polynomial of n. And this is quite long. So this is the longest path, and the story was also quite long for this path. So basically, yes, yesterday I gave you an exercise to think, well, if you can do anything better than the brute force n power k algorithm. Right, and actually, there's also a history of other people who were trying to obtain such type of algorithms. So in 1982, Burkhard Manin obtained an algorithm k power k of running time k power k. And actually, he was using a kind of representative sets, but he didn't use Balabash lemma, and this is why it's k power k. Then Hans Batlander in 1984 also observed that by making use of Trivets techniques, one can also obtain an algorithm of running time k power k. And then in 1996, in a very influential paper, so Christos Papadimitriou and Michalis Yanakakis, so they actually asked this question. So it looks like so basically, so the essence of the question was if it's possible to find a path of length k in a graph in polynomial time when k is at most logarithm of n. And of course, if I give you algorithm of running time c to the k, where c is some constant, this will immediately answer this question as yes. And the answer to this question was found it's in an extremely influential and beautiful paper, which also introduces the technique of color coding. So this is the paper of Noga, Alon, Rafael Yusta, and Uri Cevik. So, and that was a big breakthrough in the area. So they give an algorithm of running time, some c to the k, some constant c. And also there was a lot of, actually after that, that was not the end of the story, because basically there was a lot of work in parameterized algorithms, or also in graph algorithms. People were introducing different techniques for longest path. And so that's just, there was a lot of work happening. And what I will tell you today is just a small part of which concerns how to search for longest path by making use of representative sets. Okay, but before that, so basically, let me just start from the very classical. That's probably the first graph algorithms, or the ever. So this is the algorithm. It's called held carp, but it's also it seems that Bellman also independently obtained this result. So that was one of the first applications of dynamic programming. So this is the algorithm which solves so you can solve trivial salesman, but for us it's just, let's just solve a Hamiltonian path in time 2 to the n. N is the number of vertices. Yes, so the trivial algorithm. So if I want to find a path on n vertices in a graph, right? So trivial algorithm will be, I just try all possible permutations, which will be n factorial. Right, but you can do it in 2 to the n, and the algorithm is based on dynamic programming. And this is the algorithm which you use very often if you have a class on algorithms. This is one of the first examples of how dynamic programming works. Okay, so the algorithm is doing the following. So as usual in the dynamic programming, we fill the table, right? So the table of size n times n, right? So the rows of the table corresponds to the vertices of the graph, and the columns corresponds to the length of the path. And in the cell vji of the table, I want to keep vertex sets of paths of length exactly I, which ends in vertex vj. Right. So again, so the trick, as the usual thing in dynamic programming, I don't want to keep all paths, right? That will be too much, all permutations that will end up in n factorial to keep them, but I keep possible vertex subsets here. Yes, so I'm keeping sets, vertex sets, not sequences. Yes, and now how I update my table of dynamic programming. Well, first of all, I initialize the table. So in the first column, of course, all paths of length 1, sorry, not of length 1, all paths which contains one vertex, right? So all paths which contains one vertex, this is exactly vertex vj. So in the first column, I just fill the cells of the matrix by the same vertices, right? Now I proceed to fill the table column by column. So if I have a cell vj and I, so how I fill this table, right? So what I need to do, right? So if I know that there is a path of length I which ends up in vj, right? If and only if there is for some set of vertices which doesn't include vj, there is a path of length I minus 1, which ends up in vertex vk, and this vertex vk is adjacent to vj, right? So then I just, but all this information is kept in this table, right? Because in each of this table, in each column of this matrix, I keep all possible sets of with this property, right? So I just look through all I minus 1, the column I minus 1, and I compute the sets for this column, right? So once again, so the value of this column, so it's vertex sets of I minus of paths of with I minus 1 vertices, which avoid vertex Vj and which ends in vertex Vk, which is adjacent to the vertex Vj. Okay, so this is the algorithm runs in so this algorithm runs in time 2 to the n. So why? Because the size of the table is n square, right? And in every cell I keep subsets. So I go through all possible vertex subsets of the graph. So I have n vertices, and the number of all possible subsets of the vertex set is 2 power n. So this is the dynamic programming algorithm. Okay, so now let's change the game. Right now, suppose I want to find a k path. Well, so what I have to do, right? I don't have to compute the whole table, right? So then I can stop at the column, at the kth column of the table. However, but how much do I need to how much inform or how many sets I have to keep? So if I'm doing, and if I just stop here, well, I have to keep n choose k, right? So just I'm keeping all sets of size at most, vertex sets of size at most k. So at the end, I'm keeping n choose k, and every time when I need to update the table, so this goes in polynomial time. Okay, so and n choose k, so it's roughly like n power k algorithm, but it's not 4 to the k, right? It's not 100 to the k. It's something which much larger. And then the idea is, okay, so what do we have, right? So we have an algorithm. So if I just take Hell, Karp, and Bellman dynamic programming algorithm and make it only and fill the table only up to the kth column, right? So then I can do it in time n power k, right? So I keep n choose k sets, and every time when I need to update, I just have to go through the neighborhood of the vertex. So it's like n choose k times n. Now I want to use representative sets. To improve the running time of the algorithm from n to the k to 4 power k times some small polynomial of n. And what I want to do, instead of keeping n choose k sets, I want to keep 2 power k times log n sets. And for update time, instead of n choose k, I will spend a bit more here. So I will spend time to 2 power k times 2 power k roughly, and then some polynomial of n. Okay, so this is the plan, and basically, so what? So I just need to construct what are my families of sets, and I also need to define what I want to represent. Okay, so what? But here the choice is quite intuitive, right? So when I compute the value of the cell f of v, j, and I, so these are the vertex sets of I. It's a vertex set of size I, which contain a path or which goes through all the vertices in the set and which ends up in the vertex Vj, right? So this is the vertex sets of all I paths that end up with the vertex Vj. Okay, so if I have in my graph a path of length k, right? So then this path, if I can continue this some path of length I, which ends up in vertex Vj, right? Then I can add to this path k minus I should be able to add to this path or to this vertex set k minus I new edges, right? So then this is what I want to do. So I want to, as a representative, as a family of sets, I want to keep all this red paths, and then they should represent all sets, all the blue paths or all paths of size k minus I. Yes, so I just and then I want to compute the family f prime, vj, and I. So this is the family of sets which k minus I represent the family of the sets f of j I. And to do this, I just want to use the algorithm for constructing representative sets. So I want to output, yes. Yes, so I want to output. So when I have a family F, I want to output the new representative family of size 2 power k times log n, and the running time to find this representative set. Then it will be the size of the set of the family representative family here F 2 power k log n, and which is n choose k to k log n. But if I'm doing this, right, so then, well, I'm almost there, right? But still, this is not what I really want, right? Because with this running time, n choose k is of order n power k, right? And I don't want to have n power k. I want to have some constant power k. So this is not what we shoot for, but we are very close to that, right? And the reason here is like what. So once again, so what I'm trying to do. I have a family of sets here, right? And the size of this family is n choose k times 2 power k, right? And I want to use representative sets and to compress it. Right, and the only reason why my running time is so bad is just because the size of the family which I want to compress is too large. But it's too large for no reason, right? Because actually I can do dynamic programming, and I can when I fill the tables or when I fill the cells in my table, I just can do the compression step or call the representative set algorithms every time, and keep only the compressed size of the instances. And with that, I will win, and I will have an algorithm of nice running time. So. Yes. So once again, so then I just formally, so that was the intuition. Now formally, what is the algorithm for? Yeah. So yeah. So there is a question, but you don't have the entire set of F. You only kept the representative in each cell. Yes, this is true. This is what I want to do, right? But so far, so if it's just what I was saying, that if I just take the Karp-Bellman algorithm, and I just start to apply to each cell the representative set algorithms, this will not work, right? Because I cannot guarantee that I cannot control the size of the family. So I have to be a little bit more careful, right? So this is what I will explain now. Okay, so what I'm doing, so basically the idea I'm doing, so when I'm doing dynamic programming, I do a step of dynamic programming, I compute representative steps, then again I go to I make a new step, and then again, so at every step I'm calling the representative set algorithms, and because of that I do not increase a lot the size or the size of the family, and this is and then the representative set algorithms will be efficient. Okay, so this is what I'm doing. So I define, so I start from the first column. This is exactly the same as in the Held-Karp algorithm, right? Now what I'm doing, so inductively I define the set X of Vj and I, and the set Vj and I, this is again, so these are all possible sets which can be obtained from the previous cells. So this is the meaning here is that I take all sets with I-1 vertices with which ends up in Vk, and such that Vk is adjacent to the vertex Vj, and all the sets should not contain the set Vj, where f prime is defined as the following set. I just take the set X Vj I, and I use representative set algorithm to reduce it. So this is the representative set of the set X. So I'm doing the computation within two levels. I update, reduce, update, reduce. Yes. So Okay, so then is the algorithm clear, or any questions about the algorithm? Okay, so once again, I'm just doing dynamic programming. However, when I compute the new, when I'm doing computation for the new cell, I compute the sets for the new cell not from the sets of dynamic programming of head, and carp, but I already compute only, so I compute the value in the new cell from the values of the representative sets of the previous cells. Okay, so what is the running time of this? Okay, so the running time to compute a set X, right? So what I'm is because I know that the size of the f prime is 2 power k, right? So then I just go through all sets of size 2 power k, and I also try to go through the to add a new vertex, right? So then this running time is 2 power k, roughly n times log n, right? And because I'm computing a representative set, I compute the set whose size is 2 power k. This is what we compute. But now the running time is not the f times 2 to the k, but it's only x times 2 to the k. And because the size of x is now of order 2 to the k, the total running time of the update state is 2 to the k times 2 to the k. So this is 4 to the k. Right? So this is the algorithm. Right? So this algorithm runs in time 4 to the k. So the only thing which is missing so far is why what I compute is correct. So okay, so the question is why in the update state you don't have polylog factors accumulated. They don't, right? Because basically what yes, they don't, right? Because so what happened, right? So every time I compute a representative set of the family, right? And so this n and this log n is the size of the initial of the total set, right? So they will never be accumulated. Okay, so this is yeah, so on the correctness of the algorithms, yes, so why the algorithm is correct? Just so to show that the algorithm is correct, we have to show that the set f prime, which we compute, right? So the set v prime of v, j, and I, that it's k minus I represent the set f, right? And so this is what we have to show by assuming the induction assumption that the set f prime of v of k and I minus 1, that it's also I minus k minus I plus 1, it represents the set f of k, right? So yeah, so the induction assumption definitely it works for the case for I equal to 1, right? Because every vertex represents it, so all sets are of size 1, and we keep all of them. Yes. So now, yeah. So and then so what's happening once again? So our procedure is the following. So here we keep all representative sets here, right? And then okay. Just sorry. So Reinhold, once again, answering your question, while in the update state you don't have polylog factors accumulating, right? So polylog factors and polynomial factors, right? These are the factors of the universal set, right? So this is the from 1 to n, right? So they never change; they always the same. Right? So every time I call, so the number of elements in the set, they never grow up. It's always the same, right? So it's just so this logarithm is just doesn't accumulate at all. Okay, so yes, so coming back to how this so how our algorithm works, right? So in the column I-1, we keep all representative sets for this entries, and then we compute the set X there by trying to extend all these sets, and then we do compute the representative sets here, right? Right. So by definition of the set F prime, that's how we define it, right? This is the K-1 representation of the set X of V, J, and I. Right? Now, so what I want to prove? I want to prove that the set X, V, J, I, K-I represents the set F. One set represents the other set represents the third set. But because this is a transitive relation, this also will show that the set F prime represents the set, the family F prime represents the family F. So this is my plan, right? And just so let's try to prove it by definition, right? So suppose I have a set B of size K minus I, and this is the set such that for some set I from the family F of Vji, A is disjoint with B. Right? So the situation here is the following on this picture. So I have a set A, which is disjoint from some set B. This set B is of size K minus 1. This set A is from size I. Right. So what does it mean that this set belongs to this family? Right. It means that there by definition, right. So there is a path which ends up in vertex VG, and the length of this path is, and this path uses all I vertices of the set A. But then, so if there is such a path, then there exists a vertex Vk, right? So the vertex next to vertex Vj, or the vertex preceding vertex Vj on some path, right? So then there exists a vertex Vk, and there exists a set of vertices of size I minus 1, such that in this set there is a path with I minus 1 vertices, which ends up in vertex Vk. Right, and because actually this set of vertices, right, it's not intersecting the set B together with Vj, right? So I just take in this picture, so these sets are disjoint. But for these sets, we can now apply induction assumption, right? So because the family F for the family F prime for sets of size I minus 1, it's representative. So it means that there exists a set S from this representative family such that this set is also disjoint with the set B plus Vj. But then I can also construct the set, if I take the set S and I take the set Vj, right? Then this set belongs to the set X Vj I minus 1. So, sorry, it should be I here. No, I minus 1. And this set is disjoint with the set B. Right, so I constructed a set, but then the set belongs to them. So it's representable by family F prime. Okay, the question is, isn't representing all sets B of size K minus I wasteful? We only need to represent the ones which corresponds to actual paths in the graph. That's an excellent question, and this is an excellent remark. Yes, this is true, but this is exactly the problem with representative sets, right? I don't know. So when I'm doing dynamic programming, right, I'm doing it from left to right. I don't know what will happen in the future. And this is because of that, I really have to be prepared for any new set D which will come. And this is how I will use so the representative sets and Balabash lemma. it will definitely will be interesting to yes, definitely in the graph, so or the set B, which will it's a prolongation of the path, and definitely it's interesting to know if it's possible to use this property, but we just don't know how to do it. And yeah, so yeah, but this is an excellent question, and yeah. But probably the best answer is just so because we don't know the future, we have to be so pessimistic. We have to be prepared for everything. But yeah, but maybe we shouldn't, right? Okay, so for further readings, so if you want to learn more about computations of representative sets, so the chapter 12.3 of the blue parameterized algorithm books is provides an introduction to this type of techniques, and also the book contains a lot of it also speaks a lot about color coding and about other different algorithms, algebraic algorithms for k-path. So that's if you want to get an introduction to this area, I would say just look into this book. Now, if you want to see the more efficient algorithms computing representative sets, then you should go to that paper, but so a warning, it could take some time to go through this paper. Okay, any questions about longest path algorithm? Because then we will move to another topic. Excellent. So our next topic, which is strongly related, it's a generalization of Balabash lemma for Metroids. And actually, of course, in mathematics or in theory, we're always happy to make generalizations, right? Sometimes it's just generalization for the sake of generalization. But here, actually, it's not true. So actually, so one thing, useful thing of this generalization, we'll be able to solve a larger class of problems for that. That's because Metroids, they capture quite, they're way more general than sets or graphs. And also, surprisingly, here, by using of Metroids, we'll be able to get another and better algorithm for computing representative sets. So here, we generalize the Balabash lemma, or we generalize representative sets and the algorithm for representative sets for Metroids for purpose. So this is yes. Okay, but maybe just before what's happening or some intuition, yes, let me just again to this silly example with the cosmonaut selection. You remember, right? We have 20 cosmonauts, and we want to form teams of these cosmonauts. Every team should contain 6 people. And the catch here, or the task here, is that we know that 3 people, we don't know who, but we know that 3 people at the end will be sick, right? And we want to form the minimum number of teams which prevents us, which will always contain all 6 healthy people in the team. Yes, so if 3 cosmonauts will be ill, will at least 1 team survive? Yes, so, but now I changed the definition. What do I mean by survive, right? So before I was just saying, okay, so the team survives if it's not hit by any sick person. Now, actually, I want to have a more general definition because like in the current situation, right? You don't know if the person is already infected or not. Right? You can probably guess, or yes, you probably, or maybe just so every cosmonaut also has a set of features, right? So this is a set of features. It's some vector attached, say, with some real numbers. And actually now what I want to, sorry. Yes, now I want to apply the method of machine learning, right? And what the methods of machine learning are doing, right? So you represent that data with encode data with the vectors, right? And then you try to do some algebraic operations to them. For example, you don't want your vectors to be linear dependent. And here I also try to apply, as a skillful data analyst, I'm trying to apply the methods of machine learning to my problem. So now what I want to do, I want to introduce one more condition to the survivor, or one more property when the team survives. So the team survives, if it's not only doesn't intersect the infected people, but also if I take the vectors which are associated with these people, then these vectors are also linearly independent, right? And yeah, sounds a bit artificial, but yeah. So if you can come out with a better example, please tell me, because yeah, I'm not entirely happy with the example. Okay. And actually, this is what Metroids will do. So will allow to generalize the definition of what means that the team survives and how the set fits. But first, a very brief and very fast introduction to Metroids. So if you never, so Metroid is a family of sets over a finite universe, and which satisfies three axioms. First axiom, empty set is in this set if the set A belongs to the set B, and B is a subset of A, then B is also belongs to the set F. And if I have two sets A and B both in F, and one cardinality of A is smaller than cardinality of B, then there is always element of B which I can add to A, and this also will be a set F. So if you never saw Metroids, just think about universe as the vectors, right, in some, say, d-dimensional space. And then the notion F is just the linear independence of these vectors, right? Then empty set is independent by definition, right? So if I have one set which is independent and I take a subset of the set, then it's also independent. And if I have two independent set and the cardinality of one is smaller than the other, right, this exchange property, then I can always take the existing element from the larger set, such that I can add to the smaller set and still it will remain linearly independent. So, but Metroids, they are generalize a lot of different things, and the terminology which I will use, I will call the universe edges of Metroid, like edges of the graph, like and then the set, the family F, I would call them independent sets of Metroids, and then the maximal independent set is the basis of Metroid, and the size of the basis, the size of the maximum independent set, is the rank of the Metroid. Yes, and if you never saw Metroid, just think about Metroids as the independent sets, linearly independent sets of vectors. Yes, so important Metroids for us will be Metroids which are representable over finite field. So again, so if you listen to the first lecture of Madhu Sudan, so when he was saying what is a finite, if you're not familiar with the finite field, then you just think about finite field as a field of modular some prime number. So this is exactly the same here. And this is the, for example, of the set of a GF4, so field with 4 elements. And for example, if you have a field with 2 elements, there's elements 0 and 1. So then the operations are the same as with reals, except that 1 plus 1 would be 0. Yes, and then so for this Metroids, so for every h of Metroids, we correspond, if we can correspond a vector v e over some field, and we declare the subsets of element of ages independent if and only if this set is linearly independent, right? As far as I have a field and as far as I have vectors, I can define what means linear independence, right? And this is what I do here. And then the question is why it's Metroid. Please check, right? So the only way to check why this is a Metroid is to go through all three axioms. And important matroids, so linear matroids. So yes, these are called linear matroids. So this is a matroids which can be represented over some finite field. And we also and then when we have this matrix of vectors, we say that M represents matroid over field F. So this is, and if matroid can be represented by some over some field, then this matroid is called linear or representable. So first, well, so the truth is that I cannot say that you never saw Metroid because you already saw Metroids in the first two lectures, and this is a Metroid called uniform Metroid. So what is a uniform Metroid? So it's a pair. So the ground sets are the ground set consists of n elements, and independent set of a Metroid, of a uniform Metroid, it consists of all sets of size at most k. Right? So, for example, in this example, I have a set U with 4 elements. If I take k2, then the Metroid U42 will be the Metroid which consists, all these sets will be independent sets of these Metroids. Right? So Metroids represents, of course, vector spaces. Metroid represents family of sets. Also, yes. So why this is a Metroid? This is again an exercise. You have to check that this sets they satisfies the three axioms of Metroids. So another famous example of Metroids is graphic Metroids. So this the elements of this of the graphic Metroids are the edges of the graph, and the set is independent if if this set induces a cyclic graph, so it doesn't contain a cycle. So if graph is connected, then the maximal independent sets are spanning trees of this graph. And again, this is also Metroid, and also this is I suggest you to check this. Okay, but what is interesting for us? So yes. So, and this is a very basic question in Metroid theorem. So if you give me a Metroid, if this is a representable Metroid or not, there are a lot of examples of Metroids which are not representable, but the interesting Metroids like graphic Metroids, uniform Metroids, transversal Metroids, so they are representable. And for us, we really, when we work with the Metroid, we really need a linear representation of the Metroid. That will be important tomorrow when I start to proving the Low's theorem. Okay, so I'm just finishing this lecture by giving you a glimpse or proof. So why uniform Metroid is representable, right? So once again, uniform Metroids, the elements, the edges of the Metroids are the elements from 1 to n, and then the set of elements is independent if the size of the set is at most k. So why this Metroid is representable? Well, I just give you a representation of this Metroid over finite field. So what I do, I just take a finite field or g of p, where p is an integer which is larger than n, right? And then with every element ei, I assign to associate with this element ei a non-zero field element alpha I, and also I associate the vector, right? So I just take, I start from 1, so I take the 0 power, first power square up to k minus 1 power of the element, so ai here, and then the representation is the following. So my claim is that this is a representation of Metroid, right? So I have to show that the corresponding vectors are independent if and only if this is an independent set in the Metroid, right? And in the Metroid, in the uniform Metroid, it means that the size of the set is at most k, right? So of course, k plus 1 columns are always linear dependent, right? Why? Because this is the matrix with k rows. So the k rank of this matrix is at most k, right? And the rows, so the row rank is always equal to the column rank, right? So this means that if I take k plus 1 columns, they always will be linearly dependent. Okay, and now we need some linear algebra. So if I take any k columns, then I will have what's called Vandermonde matrix, right? And it's an exercise to check that the determinant of the Vandermonde matrix is always this value, and this value, because all these numbers are different, the product of these values, it's non-zero also in the field. Okay, I will stop. No, I still have 15 minutes. Okay, so sorry. Yes. I just miscalculated my time. Okay, so another example, as I already told you, this is a graphic matroid. So the elements of the graphic matroids are edges of the graph, and the set is independent if it's a forest. So first of all, why this is a matroid? It's a nice exercise, and here you need so the most tricky part is to prove the exchange axiom. If you have two forests and one forest is smaller than the other forest, then you can always take h from one forest and add it to another, and the result still will be a forest. But this is if you had a first course in algorithm, maybe you remember Kruskal or a prim algorithm to compute the maximum spanning tree in the graph. And when you prove that the algorithm works, this is exactly arguments which you use there. And actually, why Kruskal algorithm works is just because it works on a matroid, so it's hidden there. But okay, but this is beyond the scope of my lecture. But it's a nice exercise, and it's less trivial exercise to prove that graphic matroid is a matroid. And the other question is why it's representable matroid, right? And but also it's quite easy, right? So why it's representable matroid? Because you always represent a graph either by adjacency matrix. It's not good, right, for represent the matroid. But also we can represent the every graph with an incidence matrix. So MST, okay, so the question is, so MST is finding the lightest bias in the weighted matroid. Exactly. And actually, there is a very nice theorem which saying that you can always, so if you have a weighted matroid and you want to find the lightest basis in a matroid, you can always use greedy algorithm to do it. That's yes, and yeah, and this is because of the third axioms of the exchange axiom of the matroid. Okay, but coming back to this slide, so why this is a matroid again? Yeah, and but why it's representable? Well, you just take instance matrix. What's the instance matrix, right? It's the matrix where I have the rows correspond to the vertices of the graph and the columns correspond to the edges of the graph, right? And there is one if an edge is incident with a vertex, right? So definitely it's representable over reals. But the funny thing is also that it's not relevant for us, but also try to play with this, try to show that actually you can represent graphic matroid over any finite field. Okay, so now the most important definition. So what is a representative set for matroids? Okay, let M be a matroid. Then I say that a set A fits to set B if the sets are disjoint, and on top of that, A union B is an independent set. Okay, so just if we remember, right? So when we translate this, yes, and I want this definition to be generalization of what we discussed before for sets. right? So then, and this the definition is definitely generalizes. It's also, or it's compatible with what we had before. So because now if for sets now I have a uniform matroid of rank A plus B, and then A set A fits the B set B if and only if they are disjoint, right? Because the sizes of this union is at most A plus B, right? So this means that these sets will be always independent. So for uniform matroid, this property is irrelevant. Okay, and then I define the representative sets for matroid the following way. So I have a matroid, and I have a family of sets of size A of elements or of edges of this matroid M. And then I say that subfamily F prime B represents family F if for every set B of size B, sets of elements of the matroids, such that there exists a set A that fits B. This also implies that there exists a set A prime from F prime, which fits B. So it's exactly the same definition as the definition for sets. The only property that I say instead of the sets are disjoint, I say that they fit. And fit in the language of matroid means that they are disjoint plus they are linearly, so the union is linearly independent. Right? And if I transfer this definition of representative sets, or if I transfer the definition of representative sets for matroids to representative sets for sets, or for uniform matroids, right? In this case, that will be exactly the same definition which I used today and yesterday. Yes, and now I am ready to state the beautiful result of Leslie laws from, I think, from 1974 or 75. So basically, okay, so basically what Lova's proof, so here prove exactly the same or even more general conditions on but the value of but the same results as was two family of sets of Balabash. So this exactly the same condition holds for the matroids. But what I want to prove, so I don't want to prove the lowest, well, what I will prove, if we prove this lemma, it also will prove combinatorial result of lowest. But I want to prove the algorithmic statement, or here is the algorithmic statement of the theorem of lowest. Okay, so there is an algorithm. So the theorem. So there is an algorithm that for a given matrix M over finite field, which represents some matroid M of rank K. And if you give me a set of families A, so the families, the sets of size A from of independent sets from this matroid, and also an integer B, such that the sum of A and B is equal to K, so the rank of the matroids. Then, so this is okay. So once again, so the input is matroid, matrix representing matroid, and then the family of sets of size A, right? And then what the algorithm does, it computes a B representative family A prime of this matroid. So the size of this family is at most A plus B, choose A. And then the running time of the algorithm is roughly the size of the family A times A plus B, choose B, times B power omega, where omega is the matrix multiplication constant, plus A plus B, choose B, omega minus 1. And here, because I'm working in the finite field, it's just the number I estimate it's not the running time, or I estimate the running time in the number of operations over the finite field, right? Because it's the number of multiplications and summations yeah, so required to do the computation in this field. So if you speak about running time, then you have to also add the logarithm of s here. Okay, so first of all, let's just try to stare a little bit what this theorem does, right? So first of all, it actually shows that there always exists a family of such size, right? This is and this is what I call generalization of Balabash lemma, right? Because Balabash lemma says that there always exists a representative set of size a plus b choose a, and here we say exactly the same, that there exists a representative sets of size a plus b choose a, but for Metroids, so it's more general, right? And also the running time, which is required to compute this or to find this set, is oops. Sorry. Yep. So this running time, it's polynomial in the input length, right? Look, so again, a plus b choose b, because it's the size of the subfamily of the set A, of the family A. This size is always at most family A, right? So B is also at most the size of the family A. So this is polynomial, and this is also polynomial, right? In the size of the family A. So everything here is polynomial, and this is the first polynomial algorithm to compute a representative set. And actually, so the funny thing here is that I really need representation of Metroid. So I really need Metroid to have such an algorithm of such running time. So I don't know any other algorithm which computes the representative set in polynomial time and which is not based on the algebraic tricks. So this is the surprising things, and this is so the real power of algebraic methods. So I will start to, yes, so this is everything is polynomial in A. So this is quite surprising, and the proof is also quite nice. And yes, so we will start from this proof tomorrow. So I will prove you this. No, tomorrow we will not do this anything. So on Friday, I will prove you this theorem. And also I will give you one or two applications of this really nice theorem. Yes, please, if any questions. Okay, so there's a comment. So for universal families, you get a better bound for small a and large b. Yes. So the truth is that the previous algorithm, right, for some values a and b, it's better than this running time. But if you take the diverse situation, then it's this algorithm is polynomial, right? And that was not. But again, so if you want to use application like for Hamiltonian path, yes, definitely you have to use. It's better to use the previous algorithm. Right? Now, for the could you upload the slides again? Yes, I will do it, and I'm sorry I forgot to do it today, so I will do it immediately right after the lecture. Yes.
Yeah. Thank you very much for the lecture.
There's one more question. In which paper does the theorem appears? So it appears in the paper which is in the references. So so a few slides back. Yes. So this algorithm using Metroid appears in this paper. But also it's described in this book. So this algorithm is now everywhere. Yeah. Yeah.
Yeah.
Yeah.
Okay.
Please. Sorry, Mehdi. Yeah.